looked only at linear functions so far, right? All of our equations that we write as y equals mx plus b are linear functions. So linear functions are functions that form a keyword here, line. Nonlinear functions do not form a line, all right? So linear functions have a constant rate of change and form a line. Nonlinear do not have a constant rate of change and can be curved. All right, so we're still talking about only functions, so they have to be functions. But within functions, we have classifications, right? So if we look at this real quick, we have function, not a function. All right, and then within function, we have linear and nonlinear. All right, so that's like our little tree a little bit. And just as a reminder, not a function means cheating x's or not passing the vertical line test. Right, and I'm just going to do a little graph sketch right here. So an example of a linear, right, it's just an equation that forms a line. Example of a nonlinear, you might have seen graphs like this before. Might be something like this. Still a function, but not a line. Okay, so there are three ways that we have looked at linear functions. We've looked at tables, equations, and graphs. So that means from a table, an equation, or a graph, we need to be able to determine whether or not it's linear or nonlinear. So starting with equations, linear looks like dot, dot, dot. Y equals mx plus b. Or one that we haven't really looked at yet, but we're going to look at it like next week probably, or the following week, the week right before we go for break. Standard form, which is ax plus by equals c. The key here is both x and y are only to the first power, right? Remember, anything that doesn't have a power on it, it's like you could put like a little power 1. You don't see it necessarily, but it's there, right? So anything that could be written like either one of these. So essentially, when you're looking at your function, your equation, if you ever see an exponent on x or y, or a square root, then it's nonlinear. All right, so examples of both of these guys, we have y equals 1/2 x plus 4, or 3x plus 2y equals -5, right? Something like that. Oh, you can't see what I'm writing. Keeping in mind that this one can also be written as y equals x over 2 plus 4, right? That's fine. These are all examples of linear. All right, so it does not look like, and these are just going to be some examples of nonlinears. Y equals x squared plus 4. Yeah, sorry, I know I'm going fast. All right, it also doesn't look like y equals the square root of x minus 7. Or, minor change from this one right here, y equals 2 over x plus 4. Right, so in this case, x is in the denominator. So we're not multiplying anymore like we are here. We're dividing, so that means that this is not linear. So anything that doesn't look like one of these is nonlinear. And you could always test it by using the Desmos calculator and typing in the equation they give you, and you can see what they look like, and you can see that they are, in fact, not a line. Okay, so that's it for equations. Next, we're going to do graphs, which are super self-explanatory. All right, linear looks like All right, those are all the different kinds of linear functions. Just straight lines. You might want to add yourself a little reminder. Not a function at all, so it's not even classified, is a vertical line. Okay? And then it does not look like oops, that was not supposed to be my arrow. My bad. This or this or this or anything else that's just like not a straight line, right? If you look at it and it doesn't look like one of these three, then it's nonlinear. Okay, the graphs are the easiest to distinguish. You just look at them and you know, like, that's linear or that's not linear. Okay, and then the last one we're going to look at is tables. Okay, and tables are really, they're not tricky, but you actually have to do something to determine whether they're linear or nonlinear. All right, so tables. Okay, that's fine. But, so for tables, we have our X, we have our Y. Let's say we have -1, 0, 1, and then 3, for example. All right, and then we have -2, 0, 2, and 6. Okay, so when we get a table, all we have to do is find the slope between every single set of points. So I start from -1 to 0, and that means I added 1. And from -2 to 0, I added 2. So the slope on this first row is 2 over 1, which is just 2. And then I do the next row. from 0 to 1. Again, I added 1, I added 2, 2 over 1 equals 2. And then I do the last row. 1 to 3, I added 2. 2 to 6, I added 4. 4 over 2 still simplifies to 2. Now, the key right here is that the rate of change is constant, right? It stayed 2 every single time. So that means that this table right here is linear. Right? Because the slope is the same between every set of points. That's what makes a linear function linear, is the slope staying the same. Well, my thing is so zoomed in and I don't know how to make it zoom out. So let's just do this. There we go. Alright, that's a little better. Okay. So our next one we're going to do, let's just copy a table again, X, Y. Let's say we have Alright, so I have -2, -1, 0, 1, and then I have 4, 1, 0, 1. Okay, so we do the exact same thing. We check our slope. From -2 to -1, I added 1. From 4 to 1, I subtracted 3. So -3 over 1 is -3. From -1 to 0, I added 1, and from 1 to 0, I subtracted 1. So -1 over 1 is -1. And we can stop right there, because we already see that the rate of change is not the same. So therefore, this table is nonlinear. Thank you. Yeah, I hope so, Delmer. I hope it is simple enough. Right? This should be a fairly simple skill. The only thing that I will tell you is if they give you like a list of ordered pairs. So say, for example, you get a problem like, oh, my thingy is just not happy with me today. Okay. So say they give you a problem where it's like 1, 7, 2, 10, 3, 13, All right, so instead of giving you a table, graph, or equation, they give it to you like this as a list of points. I would always, always just make it a table. So I'd have 1, 7, 2, 10, 3, 13. It's just easier to see that way, which is just, I think, a little bit more helpful, so that then I could do my plus 1, plus 3, plus 1, plus 3. So again, I get 3 over 1, 3 over 1. That checks, so this is linear.